Alright, so we're gonna try floating point, sine and exponent and mantissa one more time. Well, according to log on to IT for CSEC. So let's go. Alright, so floating point numbers. So over here, we're just talking about floating point as in what you're used to in base 10. Now, over here we have an example. Consider the decimal number 5.6437 times 10 to the 4th. The number is positive, which you know is a sign. The fractional part, 5.64367, is called the mantissa. The base is 10. The power to which the base is raised is called the exponent, and that is 4. The number 5.64367 times 10 to the 4th can therefore be represented as sine, which is positive, the exponent 4, and the mantissa, which is 5.64367. So now let's now look at binary fractions. So binary fractions can be stored using a similar format of sine, exponent, and mantissa. That's SEM. Computers use different amount of bits to store floating point numbers. Most computers use the IEEE standard, which allocates 32 bits for single precision and 64 bits for double precision. This is more complicated than we need for our purposes at present. So, our example, we will use 8 bits to represent a number using the following convention. So we have 1 bit sine, 3 bits exponent, and 4 bits mantissa. Let's consider an example now. So consider the binary number 11.11, and that's base 2. This could be written as 0.1111 times 2 to the 2nd power. The process of shifting the binary point and multiplying by a power of 2 is called normalization. This is similar to writing a base 10 number in standard form. Generally, when we shift a floating point number, we shift the binary point so that it is immediately to the left of the leading 1. That is 11.11 becomes 0.1111 times 2 to the 2. Unless the number stored is 0. This is done to ensure the maximum utilization of the available memory space. We will also use the following convention for the sign bit, 0 for positive and 1 for negative. To represent positive and negative exponents, the exponent will be represented using sign and magnitude representation. And I think that is where we were having it. We weren't understanding. I wasn't understanding that part of it. So we're going to use sign and magnitude to do the exponent. Well, according to this book. Alright, so let's look at the example that they have here now. So we have, using the same example that we've been working with, we have we want to store 11.11 base 2 using the sine, exponent, and mantissa format. So step 1 would be to normalize the mantissa. This gives 0.1111 times 2 to the 2, because we move the decimal point 2 places. So remember, it is 11.11, and we are moving the decimal point 2 places. So that's 1, 2. So that is how we get the 2 here. Step 2, the exponent is 2, which is, so we're representing the 2 in binary, and remember we're using sign and magnitude, and we know that 2 is going to be, when we put that in our table, 1, 2, 4, 8, the 1 would go here, 0 would go there, and we're using 3 bits, so we need another bit, which is going to be the sign bit. It's a positive number, so that is going to be 0. So the exponent becomes 0, 1, 0. We put that all together now, we'll get, well, step 3, the number is positive, the sign bit is therefore 0. So we'll put a 0 for the sign here. And we worked out the exponent to be 0, 1, 0. And we are left with the 4 ones that we had when we moved the point. So that gives us 1, 1, 1, 1. So the full answer here is 0, 0, 1, 0, 1, 1, 1, 1. So that's how we work out our sine, exponent, and mantissa. Alright, so another example here, represent 5.5 base 10 using sine, exponent, and mantissa. We can represent 5 to the 10, so we work out the fractional part, the whole number part, sorry, which when we put that in our table, we'll get 1, 0, 1, which is 5. So 1, 2, 4, 8. So 1 here, 0, and 1. When we add that together, we get back 5. So that's 1, 0, 1, which would represent the 5. 0.5 can be represented as 0.1 in binary fraction, as you so that would be